Okay, so here we've got this 260 gram block, or mass M we'll call it, dropped onto a relaxed vertical spring that has a spring constant of K equals 2.5 newtons per centimeter. It becomes attached to the spring and compresses the spring 14 centimeters before momentarily stopping. So the first thing we want to find out is, while it's being compressed, what work is done on the block by the gravitational force on it. So let's say this block starts, and I apologize for the hideously discolored stuff, but what can I do? So it starts just as it hits the block, and then so we'll make this like a rest length for the block, and then at some time later it's compressed the block a distance, we'll call this d. Okay, so there we go, that'll work well. And there's the block with a mass of m, and there's the compressed spring with a spring constant of k. And we want to find out what is the work done by gravity on the block. Well, work done by gravity is going to equal the force of gravity, which is mg. So gravity is just mg going downward on the block, and gravity is acting in the same direction as the displacement of the block. So the work there is simply going to be mg times this displacement d. That's the work done by gravity as it goes down. Pretty darn easy, I think, unless I'm screwing something up. So let's see. 0.260 kilograms. Okay, but it's 260 grams. 0.260 kilograms is mass times 9.81 is g, and then the height it goes down, or the height it loses, is 0.14 meters. So it should be 0.357 joules. Let's hope I got that right. And of course we have to scroll all the way down. Yay! All right. So good for Dr. Smith getting one right. So now, what work is done by the block by the spring force while the spring is being compressed? Okay. Now here we've got to look at the work done by the spring as it goes from this compression 0 to this compression d. Well, the work done by the spring in this period, we'll do purple. Why not? Okay. So that's one. Work done by the spring. So I'm gonna call this like stage 1, like just before it hits the block. Really, stage 1 is like right there. Okay, and then this is stage 2 where it's come to a stop. V equals 0. So let me just do. In fact, let me do it in black. So stage 1, Ek equals some initial Ek. Okay. Potential energy due to gravity. I'm going to make this 0 thing my potential energy due to gravity, okay? So this line, when it first hits, it has 0 potential energy due to gravity, and potential energy from the spring is 0, okay? At point 2, kinetic energy I'm going to find to be 0. Potential energy from gravity, I'm going to say, well, it's going down now, right? So I said this is 0, so it's gone from a height of 0 to a height of negative d, which means the potential energy due to gravity must be negative mgd. Yeah, negative. But you can have a negative potential energy. In fact, frequently we do things where potential energy is always negative. Doesn't matter. All that matters is the difference of potential energy. So negative potential energy is perfectly legal. And then potential energy in the spring is going to be here. It's been compressed by distance d. So the potential energy of the spring, we just use our spring potential energy formula, 1/2 kd squared. So now our total mechanical energy, well, here's the thing. So actually, what we need to know now, the work done by the spring is going to be the change, let's see, the change in its potential energy, or it's going to be its potential energy at state 1 minus its potential energy at state 2. So the work done by the spring on the block, this is what we're finding, is going to equal this potential energy of the spring, 0, because remember, this is what we're saying. It's like the spring is storing up energy from the block. So minus 1/2 kd squared. So the answer is just negative 1/2 kd squared. And it's because the energy is flowing from the block into the spring. So the spring is doing negative work on the block because it is sapping the block's energy. The block goes from having kinetic energy here when it first hits to having none here, and that's mainly because the spring, well, in fact, it's entirely because the spring has sapped it away. So negative 1/2 kd squared should be our work done by the spring. So let's see, negative 0.5, No, don't put answer in there. Okay, negative 0.5 times k, which is 2.5. Okay, now this is where we get tricky. 2.5 newtons per centimeter. Yeah, newtons per centimeter. They're being tricky. So 2.5 newtons per centimeter. I'm going to go ahead and convert this to meters. Would really be 250 newtons per meter, okay? Times 0.14 squared, because that's our d, and we square it. So negative 2.45 joules. Let's hope I got that right. And yes, okay. So part C, so we want to find the speed of the block just before it hits the spring. So now what we have is we know this. We know the total mechanical energy here in this state is 1/2 k d squared minus mgd. Okay, and the total mechanical energy in this state, or sorry, E mech, is just initial kinetic energy, and so, which is really just 1/2 mv naught squared. Okay, so here's what we do. We set these two equal. We're going to say it's conserved because it is. So we say 1/2 mv naught squared equals 1/2 k d squared minus mgd. So now how do we solve this? Well, we want to solve this for v naught, right? So we actually just calculate what this is, and then we can, so really v naught squared is going to equal 2 over m times k d squared minus mgd. So, and these were actually our answers for the negatives of our answers. Oh, hold on, this is a 1/2 kd squared. My bad. Okay, so these were actually our answers for the previous ones, but the negatives of them. So let's see, our kd squared, or 1/2 kd squared, would be positive 2.45. Okay, and then our negative mgd would be negative 0.357. Okay, and then we take that and we multiply that by 2. Let's see, is this right? Right, multiply. So this is what we have now. Multiply that by 2 over m, and let's see, 2, yes, divided by 0.260, and that should equal the square of our velocity, our initial velocity. So I'm going to take the square root of that. So throwing everything in all this, and this should be our actual answer, 4.01 meters per second. Let's see how we do. And unbelievable how lucky I'm getting. Okay, finally, if the speed at impact is doubled, what is the maximum compression of the spring? So now we're actually taking this same equation here, but we want to we want to now do it with double the v naught, and then try to find what the change in the spring compression is. So, oh man. So let's see. What we want to do is, let's take this a little bit here and do v naught squared equals, we can cancel these 2's here, so we can make this k over m times d squared. That's what this term ends up being, minus, and then this is 2 over m times negative m, so minus 2g times d. Okay, so we're going to put this in quadratic form and say we're solving for d, remember, so k over m times d squared minus 2g times d minus v naught squared equals 0. And then I'm just going to go up here and do it up there instead of to get more space down there. So let's switch to, I don't know, orange, yeah. Let's do d equals negative b, so it's going to be 2g plus or minus square root of b squared, so that's going to be 4g squared. Hoo boy, minus b squared minus 4ac, so that's going to be actually a plus 4 k over m v naught squared. Jesus, all right. So let's see, plus 4 k over m times v naught squared. Okay, this is k over m times v naught squared. I know it's hard to read. Sorry about that. All over 2a. So all over 2k over m. So first let's talk about these 2's here. Let's switch to green now. Actually, let's switch to blue. Okay, so let's talk about these 2's here. This 2 can cancel out. This 2 would cancel out with the square root of 4 and with this square root of 4. So that makes our equation a little easier. So what I'm actually going to do is I'm going to go ahead and divide this into here. So this is going to be mg over k plus or minus, and then for this term, square root of, and then we'd have to square this to put it inside. So m squared g squared over k squared, and then m squared, and this is k over m, right? So this is actually plus m over k v naught squared. Oh boy. Wow. Okay. So this should hopefully give us something like an answer. My gosh, if we plug stuff in. So let's see. Our mass was 0.260. So I'm going to say, I'm going to call m, I'm going to say, I don't know, I'm going to say A equals mg over k, which is going to equal 0.260, no, 260 times 9.81 divided by 250 was our k for this, right? Yes, okay. So that's our A. Okay, and A is what? Okay, great. And then, okay, so then we're going to have A plus square root of A squared plus m over k, 0.260 divided by k was 250 times, and what was our v naught? Oh, it was twice our, twice 4.01, so 8.02. That's 8.02 squared. Hopefully this will give us, and so what this gives us is 0.269 meters, or 0.27 meters. 0.269 meters of compression. Let's hope that's right. And let's go to number 4, and oh my gosh, I can't believe I got it right. So painful and annoying, but it does give you the right answer in the end. This is your distance compressed as a function of V naught. So this is when you plug in twice your other V naught into this. So there you go. Ugh.